All right, so you got a chi-square distribution, and one thing that follows chi-square distribution is this, the score that deals with differences between what we see and what we expected to see. Now, obviously, I like this example because if you roll a die 60 times, are you going to get what is theoretically predicted? What is theoretically predicted? What would you exactly expect to have happen? If this is a fair die, there should be how many ones? You could do it. You could do it 60 times, 6 things. If it's a fair die, should any of them show up more often than the other ones?
No.
So how many of each would there be? 10. Good. This is an example of a uniform distribution, right? Now, obviously, even if the die is fair, if one of them is not 10, are we going to go, oh, no, screw you, no. You've weighted your die. Get away from me. Are we going to do that? Of course not. So this is the idea of, is it far enough away from what we expect? Again, the same language of hypothesis test, but I think with this it actually makes even a little more sense. We expect it to look like, this is what we observe, we expect it to look like 10, 10, 10, 10, 10, 10. Yes, sir?
These aren't the exact numbers from the homework, right? Or yeah.
No. Yeah, there was a problem with this in the homework, but no, I just made these up. That would really freak me out if they were the same. I'd be some weird psychic link with the book. I don't want that to happen. I don't need that. Psychic link with the book. Alright. You guys with me? I mean, this is theoretically what we'd expect. If I got a 9 there and an 11 there, even a 13 somewhere, I wouldn't freak out. This is you see that 5 there? It's like, now I'm like, is that enough evidence? Is that enough evidence to say that this die has been tampered with? You guys start to see what's happening. So there's a mathematical way to determine what enough evidence is. Maybe. Right. It's the whole idea that we've had for a long time about unusual. It's what the hypothesis tests were all based on. How far away is it from what we expect to see? So this score here, and again, last time I talked about how that's very related to the z-score formula. Taking this stuff and transforming it into this score so I can look at it in the chart. I can compare it to the values in the chart. I like it. So to do this, I really just make a table of observed minus expected. Let's try to do this. Observed minus expected square. Let's see if we can do that. 1, 2, 3, 4, 5, 6. For the ones, yeah, 15 minus 10, 5 squared is 25. For the 2s, 4. 25 again, right? You guys, everybody see what's happening? 5 minus 10 is negative 5 squared is 25. I'm just doing this because that's what I need part of. 4. 1. Negative 1 squared is 1. Does everybody see what I just did? Not just I wrote stuff in purple, but do you see where they came from? Alright. Now to do this, I can't add these up yet because I haven't divided by e. So this is the sum of this whole damn thing. So I need a column of those. I haven't divided by e yet. So observed minus expected squared divided by e. So just divide all these by 10. I like it. So in other cases, we saw the other day how it's not always uniformly distributed. It might be 20%, 30%, and then you have to calculate what the expected is, and then you'll be dividing by different things for each one. Uniformly distributed, hey, just divide by the same damn things. Oh, they're all the same E. So this will be 2.5, 0.4, 2.5, 0.4, 0.1, 0.1. How are we doing? You all right? Everything's happening. I have a question for me. Okay, so then you add these up I love chi-square. I said it was chi-square critical because I don't want to put little stars. I'm going to do what the book does. It's called a chi-square. Actually, I think the book says, I don't know what the book says for this, to be honest. But it's going to be like my chi-square star, like Z star, right? So this chi-square is going to be used for some of these. So it looks like I get 6. So that 0 would mean what? If I got a chi-square, what's the only way I can get 0 here? I guess mathematically, because I'm squaring this stuff, the only way this can add to be 0 is if every one of these was 10. Because then the difference would be 0, and the squares would be 0, and the sum would be 0. So chi-square 0 means it follows what I expected exactly. So I'm just asking how far away from that did it get? And of course, that's why we square it for the same reason we had to square standard deviation. Because some of these are going to be negative, some are going to be positive, so I've got to square it just to do that. That's why this has got a square on it, this symbol. Don't take the square root at the end. Don't do that. Okay. Now, how do you read the chart? This is like my chi-square star. I can't remember what I said I would call this, but the chart. Who remembers, how do I calculate degrees of freedom for this?
The number of categories.
Yes. How many categories are there?
6.
Yes, they're numbered for you. 11. 6. The really sucky thing about this chart, besides the fact that it exists, and I have to tell you about it. Me, I love it, but some of you guys might go, oh God, another chart. Is that this is all about the area to the right. Whereas the z-square chart was all about the area to the left. So you just got to let go of that. When you do this kind of a test, and I'm doing alpha 0.01, a goodness of fit, a golf test, a goodness of fit, is always going to be a one-tailed test up here. It's really asking, am I far enough away from 0 to say that there does seem to be some difference? Right? So let's see, degrees of freedom for us was 5, I like it, because there's 6 categories. It's not got anything to do with this. It's got to do with the number of categories. Degrees of freedom 5, I want alpha of 0.01, so I want the area to the right to be 0.01, so it's exactly, holy crap, what did you do? Area to the right, I want it to be 0.01. That's kind of awesome. Degrees of freedom is 5, so I go plot 15.086. That's what they call the critical chi-square. That's like the rejection region. So to show evidence, my chi-square has to be greater than, what did I just say? 15.086. That's where the rejection region is. Please notice, this is nowhere near as detailed as the hypothesis tests from before. But you might see why I decided to do this after the correlation. I want to give everybody a little bit of breathing room between the hypothesis tests and this. This is nowhere near as detailed. You got this little thing to do here. You get your score. Did we make it far enough away? We made it like about here. 6. That's 15. So, did we find evidence that it doesn't follow what we expected? Or did we fail to find evidence? We failed to find evidence that this does not follow. It's not far enough away. So if it was in here, if it was there, that's evidence that it doesn't follow what I expected. It would be evidence that somebody tampered with it. Because it would be so far from what we expected, it would be a very low chance that would have just happened randomly. Same language I use when we talk about hypothesis tests. But since it was there, that's not very far away at all. That's not good enough evidence. This just happened randomly is what we're thinking. So then we'd say we did not find evidence to show it is not a fair die. Look at it. I love that. Good old double negative. Yes?
On the problem in the book, I got like the decimal for the sum up. It was like 2.26. So in that case, would I just
No. Degrees of freedom is based on the number of categories. There were 6 categories.
Sorry, for Chisquare.
Oh, no, Chisquare. No, this just happened to be 6.
Okay.
It could have been 6.18724.
Okay, that doesn't matter.
Yeah. You just have to be careful about rounding if it's really close to this, to be honest. Right? But it's nowhere near that, so who cares how much you have?
You said
Yes.
Chisquare has to be greater than 15.086.
To show evidence that it's not a fair die.
Okay.
So to show that it's not a fair die, what would it mean for it to be not a fair die? It doesn't do what we expect it to, which is evidence that somebody tampered with it. That's what it means to be not a fair die. Right? Are you with me? 2 die is dice, so die is 1 die. Right? I'm sure you guys all know. We don't all play craps. I don't play craps either. So if I would have gotten out here, it would have been evidence that what I saw was really different from what I expected. Different enough to say something is different about this die. Here, it wasn't different enough. So how do I explain the differences? Random variability. I know it's not always going to be 10, and these weren't far enough away from 10 to be evidence that it was more than just random variability. If you flip a coin 50 times and you get 30 heads, you get a freak? No. Expect 25 and you got 30. Oh my God. No, who cares? What's up, guys? Yes.
If we did find evidence to show, what could the value be? Like, you know what I mean? If we found it at 15.06, but
Yeah, our chi-square here was like 16,
so
right? If it was 16, then we would have said we have found evidence to show it's not a fair.
so we're going by the 6. That's what.
Totally. This is just like Z star, right? That is where you fell. This is how far away you got to fall to show evidence. So it feels very much like a hypothesis test. I think this is kind of nice because it's got all the most physically evident features of hypothesis test without all the extra little crap. Now, to be honest, there's a little bit more to this, obviously. We're doing this at the end of the semester. I'm not getting all that deep into it. But I at least want you guys to know that the chi-square distribution exists. Because if anyone's going to psychology or education or business, chi-square is going to possibly come up sometime. Say you got to use the right score for the right distribution. If you only know normal distribution, too bad. Here, before I forget, let me take a second to give you the practice final exam. Yeah. Oh, crap. Everybody know that Wednesday's the last day of class.
Yeah.
And then the finals are happening next week. Ours happens next week sometime.
31st.
So on this Wednesday, I'm going to have the quizzes graded. I'm going to give you an updated grade sheet. It's going to say the day and time of the final, so you guys all remember. It's on your homework sheet and your syllabus, so I don't know how you would.
The sheets that you've been giving us with the grades on it, and it's like not including
If you did more than your current grade, you know.
Yeah.
So like, somebody's got a question. I don't put the homework grade until the very end. Is that towards me or is that towards them? That was towards them, okay. Something newsworthy just happened. So, on your grade sheets, I always put not including homework, right? Okay, that's because I let people turn in late homework. You do corrections. The homework grade is always fluctuating. So, people get a little freaked out that if you got a 90 and you do all the homework, your grade would become a 90.3 or something. Like, homework doesn't do shit for me. No, homework's why you got a 90. Holy shit. But if you had 100 average, and you did all the homework, your average wouldn't change at all. Do you understand? So the higher your average is, the less effect homework's going to have. The bigger it's going to have the other way. If you did none of the homework, it's going to take you down. All right. Now I'll tell you this little secret that I don't like to tell my class too early. I don't let homework fail somebody. You understand what I'm saying? So if I average your scores before including homework and you get a 70, you passed. If I put homework in and you got a 69 or 68 or something, I'm going to count the 70 as your score. I'm going to count your test and quiz performance. Now, if you passed, if you get like a 80, but you didn't do any homework, I'm going to give you that C+. Oh, hell yes. Right? Not the B-. I let homework take you down all the time, but I don't let it fail you. Right? Because you're failing yourself already if you're not doing the homework, so I don't have to do it for you. Right? Saves me a little bit of time. All right. Maybe. Okay. So I want to do a little bit more in chapter 11. I'm not going to tell you where any of that.
You know how you have to like evenly go on both sides of the finding? You know how you get that problem where like if you got one over, you go one over the other way.
Oh, yeah. We're going to get into something like that right now. So recall how confidence intervals are made using the standard deviation, right? You guys understand what I mean? The confidence interval I would get would be created using, obviously it's using the standard deviation because it's in there. So, I can't, and of course what distribution is this using? What distribution? Sure. So the normal. I could be using T. If I put a T and an S there, it would still be the normal distribution, just the altered T-scores to cover my ass for the wrong standard deviation. You guys with me? Normal distributions are shaped based on standard deviation. If the standard deviation is big, it's fat. If it's small, it's skinny. So that's what got us into this chi-square thing. The chi-square distribution exists because it's how standard deviations fall. So if I take samples of people and I record their standard deviations, the shape is going to be like that. It's not going to be normal. It's going to be chi-square. Let that sink in. So if I take people's ages, I take 38 people at a time and I plot their ages, it's going to be normal. You with me? If I plot their means, it's the central limit theory. It's going to be normal. But the normal curve is controlled by the standard deviation. So how does the standard deviation look if I plot them? It's not going to look like this. I really hope you guys understand. I have to know the standard deviation just to get the shape of this normal curve. If I have a bunch of standard deviations, what the hell's controlling the shape now? Well, now I know it's the chi-square distribution. That's what it's going to look like. So, in the same way, I can tell you guys love this. In the same way that we have all these different z-score formulas, we have x bar minus mu x over sigma x bar, blah, blah, blah. And we have p hat minus p over square root, blah, 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 right? But they're all can refer, once we calculate it, can't we just look at the z-score chart? They start in different places. They start with percentages, they start with means and stuff. But once I think of z-score, I can look at the same chart, can't I? All right. So we have this one we just used. Yeah, become big. Okay. We got this one we just used. And there's another one. There's actually a more fundamental definition for chi-square. There's another formula, just like there's multiple formulas for z-dude. There's this guy. Make sure you guys see that's the N. So what I can do here is, if I know the population standard deviation, but I have a bunch of samples that I take, again, I can calculate a chi-square score for a single standard deviation. So it's sort of like taking a sample mean when I know the actual population mean. Taking a sample standard deviation when I know the actual population standard deviation. I can create a score just like I can create a z-score. I really want you guys to get this. So the z-score is the normal distribution, standard normal distribution. If I do this, it's very much like this, but it's going to end up with the chi-square distribution. It's going to end up looking like that. Okay. Learn to accept the non-response. The beautiful thing about this now, and some of you guys are like, okay, where the hell is this freaking confidence interval that you wrote up here, Jeff? So what I do is, if I want to be like, if I want to create a 95% confidence interval for sigma. So I don't know sigma, do I? In that case, it's creating a confidence interval for sigma. I don't know freaking sigma. But can't you solve this for sigma?
Yeah.
Right? And what we normally do, actually, we solve it for sigma squared, and at the end we take the square root. So all I have to do then is, remember that trick? So then I know sigma squared equals n minus 1 s squared over chi squared. Now here's where what you asked for comes into play. If I want a 95% confidence interval, then I want to go up and down, and I'm going to do that in the chi-squared chart now. Whee! So that there's 95% in here. This is what I was talking about when we first started talking about the chi-square distribution. The idea of the chi-square small and the chi-square big. So I really, watch me. What do we do? Stay with me. What do we do when I want to make a confidence interval for a mean? I look up two z-scores. A big one and a small one. A positive one and a negative one. Right? Are you guys with me? And that kind of bounds the middle 95%, and then I make a number here and I make a number there. Why is this formula easy? Because it's symmetric. The normal distribution is symmetric. I just need a positive z and a negative z. Is this symmetric? Does it have any chance to be really symmetric truly with the numbers? No, because that's freaking 0. Right? So even if it was symmetric, it would still be like 2 and 10, not negative 2 and positive 2. Do you guys? There can't be any negatives here. So what I'm saying now is this is the basic form of what we're going to use, but we're going to make the bottom and the top of the interval. I'm going to divide, let me see if you guys get this. The interval is going to go from n minus 1 s squared over chi squared big to n minus 1 s squared over chi squared small. Why does that make sense? When you divide by a small number, you get a bigger number, right? When you divide by a big number, you get a smaller number. So let's try an example out. Yes, Jeff, please, dear God. Something concrete in my life. Let's see. Let's remember these. Sure. Level of creativity right now. It's kind of low. Sample 41 things just laying around. We find the sample variance of 17.91. So that's for the sample. That's the sample variance. But so we're just like we find a sample mean, and they're like, where might the real mean be? We're this confident that this thing contains the real mean. We're going to construct that interval. Do the same thing now for the standard deviation. So my whole purpose at first is what's chi-square big, what's chi-square small. Now here, this is not a goodness of fit test. This doesn't have categories. So the degrees of freedom is what we're used to. What's the degrees of freedom going to be for this problem? What do you think? 40. I love it. And alpha, 95% confidence. Now, here's where drawing the picture is going to help you a lot, because this chart, not only is it the leaning chart, but it's built differently. It's all about areas to the right. So if I want a 95% confidence interval, what percentage is over here to the right of that chi-square score?
0.025.
Yeah, like 0.025, like 2.5%. And what's to the right of this one? 0.95.
0.925. No, 75.
There it is, 0.97. So this is what I was talking about. The very first thing we did was we looked here and I showed you that neat symmetry in the chart. So I want 0.025. That's going to be chi-square big, because that's the one that's got just 0.025 above it. Where am I going to stop? And then notice, I also want 0.975, and see how they're symmetric to each other. Boing, boing, boing. Just like that. You don't have to make that sound. I'm surprised I did, but oh well, it happened. So I want to go down both of these and stop. So do you notice what's happening? So instead of looking at one z-score and then putting plus or minus because it's symmetric, we have to look up 2, but thankfully the chart is symmetric for me, right? So we go down, where am I going to stop? 40. That's crazy. So I get for chi-square small, I get 24.433. For chi-square big, I get 59.342. 4.433. What'd you say, Jeff? 59.42. So then the slightly easier way to write this for this is sigma squared is going to be between. And now I'm going to use this. Right? It's going to be from chi-square big to chi-square smaller, because when you divide by a bigger number, you're going to get a smaller number. So the tops, notice, are going to be exactly the same. So this side is going to be, oh shit, yeah, good job. 21.
24.
You need that.
4 GP.
So this is going to be n minus 1, 40, times s squared, and of course we calculated s, so here's s squared, 17.91. Divided by chi-square big, which is this guy, 59.342. This side's going to be the same top, right? Same top, and then chi-square small, 24.433. So let's see, what do we get when we calculate all that stuff? Calculator? Let's see, where are we at? There it is. Divided by, where do you go? 59.342. Divided by 24.433. So is that what you guys got? 12.07 to 29.32?
Yeah.
07 to 29.321. Somebody help me out. This is where the variance is. I want to know the confidence interval for the standard deviation, so what do I do everywhere? Square root of it. So I do square root of the 29 number, I get 5.41. If I do square root of the 12.07 to 3.47 to 5.41. What was this? What's S up here? What's the square root of 17.91? Can somebody do that for me real quick? So I have to walk all the way over there. Square root of 17.91.
4.232.
So notice how 4.232 is not exactly in the middle of these. I don't know if you guys see that. 4.232 is like 0.8 above that, but it is 1.17 below that. It's not symmetric, and we know it's not symmetric because it looks like freaking Jabba the Hutt, right? If you've never seen that movie, I mean, not know what I mean when I say Jabba the Hutt.
Yeah.
What about Pizza the Hut? Anybody ever seen Pizza the Hut? Spaceballs. No? You should look that up. Spaceballs. Dark Helmet. The Schwartz. Yes, you got it. Okay. But see now, so this, we would say we are 95% confident, oops, I read the story, that the population standard deviation is, we are 95% confident that the interval 3.47 to 5.41 contains the real population standard deviation. It feels very similar to confidence intervals we've done before. I like it.
Can you repeat that last part?
Same thing, we are 95% confident that the interval of 3.47 to 5.41 contains the population standard deviation. Or whatever this is, the thing is. I like it.
Oh, okay. And that's because the sample is within the range.
Well, the sample is definitely going to be between these because of the way that this is built. It's not as obvious as the plus or minus, where of course it's going to be in the middle because I add and subtract something from it. But that's always going to be in the middle, but it's not exactly in the middle. It's going to be in between those. But it's not exactly in between those because it's not a symmetric distribution. Well, for you it's not. Yeah.
When you put 0.025 for the one tail, how come it wouldn't be 0.05?
Because if there's 95% inside, there's 5% outside. 2.5% on one side. Cool. I like it.
So the low, the small would be just 0.95? No. 0.975.
Yeah, exactly. 0.975. It pushes it all the way back here. That's why it's small and closer to zero. I like it. All right.
Do we always have to square the s? Why? I don't understand why you use square root.
Well, this one was given to me as a variance. If they gave me s, the formula requires s squared. That's all. Here I gave you s squared, so you just plop it in.
Oh.
If they would have given me s, I would have had it squared first before I plopped it.
Oh, okay.
Now, here's the part that drives me a little crazy. That was a decent little round of questions. I love that. And I'm going to make this problem an extra credit problem on the final. The only part you're responsible for in Chapter 11 is 11.2. You guys just woke up all of a sudden. It's because somehow you knew it was nothing going to be you're responsible for. I understand that. Ask that many questions on the stuff you really need. I needed to not let you leave this class without seeing this formula exists, because depending on what you use statistics for, this might be something that you've seen before. So I at least want to show you one example of this in action. So we got our practice final. I'm going to let us out now. How's that sound? So on Wednesday, please don't miss Wednesday. I'm going to have the quizzes graded. I'm going to have my finals week schedule. It's going to change because no classes next week, just finals. So my schedule's going to change. So you want to get that from me. You want to get your last grade sheet summary. You want to get the answer key for this. All kinds of shit to not miss Wednesday for. I don't know. It's on your homework sheet, your syllabus. At the moment, I do not have that in my brain at all.